Objective: to understand the hydrogen spectrum and the different series of spectral lines of the hydrogen atom. According to Bohr's theory, an electron neither emits nor absorbs energy as long as it revolves in a particular orbit. However, when an electric discharge is passed through hydrogen gas at low pressure and high temperature, a bright light is emitted by the hydrogen atoms. This light, when allowed to pass through a prism and examined using a spectrometer, a series of lines of different wavelengths are observed. The series of lines observed is called the hydrogen spectrum. Some of these lines are present in the visible region, while some others are present in the ultraviolet and infrared regions. Let's understand how these lines are formed. When an electron absorbs energy, it jumps from its ground state, which is its normal energy level, to an excited state or a higher energy level. But the lifespan of an electron in higher energy states is very short. Therefore, it returns to its ground state, making one or more leaps. During each jump, energy is emitted in the form of a photon of light, of definite wavelength or frequency. The frequency of the photon of light thus emitted depends upon the difference in energy of the two energy levels. When the emitted radiation is studied using a spectrograph, it is found to comprise a series of lines of different wavelengths. Spectral series of hydrogen atom. The hydrogen spectrum consists of Lyman series, Balmer series, Paschen series, Brackett series, and Pfund series of spectral lines, each named after their respective discoverers. Lyman series. When an electron jumps from any of the higher orbits to the first orbit, that is N2 equal to 2, 3, 4, 5, 6, 7 and so on, to N1 is equal to 1, spectral lines are formed in the ultraviolet region. This set of spectral lines is called the Lyman series. Balmer series. When an electron jumps from any of the higher orbits to the second orbit, where N2 is equal to 3, 4, 5, 6, 7 and so on, to N1 is equal to 2, the spectral lines emitted are in the visible region. This set of spectral lines is called the Balmer series. Balmer series is known to be the first series of hydrogen spectrum discovered. There are 4 prominent colored lines in the Balmer series and are designated as H-alpha, H-beta, H-gamma, and H-delta. The lines are observed to be increasingly close to each other as the wavelength decreases until a continuum is reached. The color of H-alpha line is red, H-beta line is greenish-blue, H-gamma line is blue, and H-delta line is violet. Their respective wavelengths are 6,563 angstroms, 4,861 angstroms, 4,340 angstroms, and 4,101 angstroms. Similarly, when an electron jumps from any of the higher orbits to the third, fourth, and fifth orbits, respective set of spectral lines are emitted in the infrared region. This set of spectral lines are called Paschen, Brackett, and Pfund series respectively. Wave number of spectral lines of hydrogen atom. The wave number of a spectral line of any spectral series of hydrogen atom is given by the expression 1 by lambda, which is equal to nu bar, is equal to r into 1 by n1 square minus 1 by n2 square, where nu bar stands for wave number. Lambda is the wavelength, r is called the Rydberg constant, and its value for the hydrogen atom Rh is 1,96,7 77 per centimeter, or 1.0967 into 10 raised to the power of 7 per meter. N1 takes values such as 2, 3, 4, 5 and 6 for Lyman, Balmer, Paschen, Brackett and Pfund series respectively. For a given spectral series, N2 is always greater than N1. Let's apply the formula to check the wave number of the lines of Balmer series. For this series, N1 equals to 2, N2 equals to 3. Therefore, nu bar is equal to RH into 1 by 2 square minus 1 by 3 square, that is equal to RH into 1 by 4 minus 1 by 9, which is equal to 5 RH by 36 per centimeter. Likewise, we can obtain the wave number of any line using this formula. Limiting and maximum wavelengths. It is to be noted that for any series, the line of limiting or minimum wavelength is obtained if N2 is equal to infinity. On the other hand, to obtain a line of maximum wavelength for Lyman, Balmer, Paschen, Brackett and Pfund series, the value N2 takes is 2, 3, 4, 5 and 6 respectively. Let's find the limiting and maximum wavelengths for Balmer series. For a line of limiting wavelength of Balmer series, N1 is equal to 2, N2 is equal to infinity. On substitution, we get the value of limiting wavelength to be approximately 3648 angstroms. For a line of maximum wavelength of Balmer series, N1 is equal to 2, N2 is equal to 3. On substitution, we get the value of maximum wavelength to be approximately 27,360 angstroms. Number of spectral lines of each series. The maximum number of spectral lines formed when an electron jumps from N2 state to N1 state is given by the expression N is equal to sigma N2 minus N1 is equal to N into N plus 1 divided by 2, where N is equal to N2 minus N1. Let's summarize.